Okay, I hope you're all doing well with planetary motion. I'll upload the remainder of the answer key for that later today or early tomorrow, just to make sure you're good with it. Um, for today, I want to go on to the last major topic of the chapter. Your book doesn't cover this at all, really, but I want to, so let's take a look. Um, rather than try to put together a PowerPoint like in on the fly really quickly and it'll just be garbage anyway, I decided to make a Word document where I use the equation editor so you can see the equations more clearly and you don't have to try to read my bad handwriting. Um, Today I want to revisit the gravitational potential energy. Now you'll remember back when we did energy early on, we saw that I should maybe put that in here. Potential energy U equals mgh. But that's where h is the height above the surface or whatever the object is being moved. However, that's an approximation. It only works if you don't move so far above the Earth that the value of g changes. So if I go up to a height, maybe the top of the school or the top of even the Empire State Building, the value of g is still so close to 9.81 that nothing changes, and this equation will work perfectly well. But if I'm going to launch a rocket up to 100 kilometers of altitude, the value of g up there is significantly less, and so this equation is not going to work. You're going to have to account for the fact that g is changing over the course of the launch, which for you calculus people means you're going to have to integrate. Hopefully you guys covered that by now. What I want to do is go back and remind you of the equation for the force of gravity on any object. Force is g(m)m over r squared. Capital M is the mass of the Earth. Lowercase m is the mass of the thingy you're launching. R is the radius from the center of the Earth, remember. Now, you'll recall that work is just the integral of f dx, where f is the force function. When we were doing forces, we just used constant force values, so the integral was really easy to deal with, and we didn't have to do any calculus. In this case, if I want to get the potential energy of launching a rocket, that means the amount of work I did on the rocket. And that means I'm going to have to integrate the force function, which is our gravity function that you've been using up here. I won't go through the gory calculus details because not all of you are in there. But if you've done integration, you should be able to see that if I take this function and I integrate it with respect to r is the radius, the equivalent of x, just generic distance in our discussions way back when. If you integrate this equation, you'll get the potential energy U equals negative g(m)m) over r. That negative sign comes from the negative second exponent here on radius. So this is the actual true equation for gravitational potential energy. Notice again, m is the mass of the Earth, lowercase m is the mass of the object, and r is the radius from the center of the Earth. So this is an absolute measure of energy, not the relative measure we had with mgh up here. If we were actually in class, I would take some time on the whiteboard and show you how this equation actually reduces to mgh if you're working with very, very small intervals and you can assume that g doesn't change. But when it does, you have to use this form. Notice, and again, I made a little note of this on my document. I'll upload this document so you can treasure it always, as I'm sure you will. Note that the potential energy value is negative and always will be. Okay, gravitational potential energy is always a negative value. The reason for that, let me come to my whiteboard here. If I graph energy on the y-axis and distance from the center on the x-axis, we know if you're infinitely far away from Earth, you have zero potential energy. As you move closer to Earth, your potential energy is getting smaller. As an object falls, it's losing potential. So that means the potential energy curve must be decreasing from zero, or the potential energy curve does something like this. Okay, we refer to that as a gravity well. Now, notice if you get infinitely close to the center of the Earth, your potential energy becomes negative infinity. But you can never get there because the surface of the Earth might be right here. So you can fall down the gravity well until you hit the surface of the Earth. If we could somehow compress the Earth to be smaller radius but the same mass, then you can go down further in the well. In fact, if you can collapse the Earth infinitely far and make it a point mass, you would be down here at negative infinity potential energy. Black holes end up being like that. Notice, by the way, a black hole isn't more massive than it ever was before. It's the same mass. So why can't you escape? Because when it was a large object, you were stuck here at the surface, and you could easily come up the well that small distance. If it's collapsed down to this tiny, tiny radius, you can go way down deep in the well, so deep that you're not going to be able to get out again. And we'll talk about that tomorrow when we look at escape velocity. So anyway, that's why potential energy is always negative. It always ends up down here on the negative side. Let me come back to my document. You'll see I have a million documents open. I do that. So the potential energy then is that, and it's always negative. Now, why does this matter? Because back in the day, we used conservation of energy. Kinetic initial plus potential initial equals kinetic final plus potential final. For our purposes here, we're going to ignore elastic energy because I don't think we'll be using springs to launch stuff into orbit. It might be a fun lab. But back in the good old days, K was 1/2 mv squared, U was mgh, and we just plugged in what you had, and we did stuff with, like I think we launched Zoe out of a catapult or something like that. And you could easily just plug in values and find the final h in mgh here, or find the final velocity in 1/2 mv squared there, or whatever. But now, of course, when you're launching rockets into space, mgh won't work. You have to use this negative gmm over r for your two u values. And so your equation now becomes this. Okay? This is now your new conservation of energy equation. 1/2 mv squared initial plus, or minus, because the negatives is plus and negative, so minus gmm over r initial equals the final values. Okay? Notice the mass of the object cancels out. It doesn't matter how heavy your rocket is, it's going to do the same thing. Gravity always works that way. So you can cancel out those little m's when you actually use the equation. Well, let's see here. The r value, radius, is radius from the center of the Earth. You have to remember that. If I'm launching something from the surface of the Earth, it's not launched from a height of 0. It's launched from a height of whatever the radius of the Earth is. Okay? So sample problem here. That I didn't actually solve the whole thing, but you can plug in. I'll leave that up there too. What if we launch a rocket from the surface of the Earth at a velocity of 5 kilometers per second? Notice we tend to give these things in kilometers, but you got to convert to meters. How high does it go? Well, it's going fast enough we can't use just mgh anymore. So, realize just like before, just like with launching Zoe into the air or whatever, the final velocity is 0. So up here, your final 1/2 mv squared will be 0. So plugging in, we have the initial at 1/2 mv squared, 1/2 times 5,000 squared. 5,000 because 5 kilometers is 5,000 meters. Okay, so that's the kinetic, plus the potential is negative g mass of the Earth over radius from the center of the Earth. So 6.38 times 10 to the 6th meters is the radius of the Earth. If we were launching it from some platform high above the surface, we'd have to add its height to this radius. So if I went to launch maybe from the top of Mount Everest, we would take this radius of the Earth here and add in the height of Mount Everest, and that's my actual radius that I'm launching from. Usually we just launch from the surface. So the initial condition is 1/2 mv squared, there's the 5,000 squared, plus this negative potential energy here, equals the final condition, 0 kinetic energy, because at the top of the launch it comes to a stop, plus this negative potential energy, negative g mass of the Earth over the new radius. Now, the algebra here won't be all that, as easy as just using MGH, but it's certainly doable. You can solve for the new radius. And I didn't do that because I'm lazy, but you guys can all plug into your calculators. That new radius, don't forget, is the radius from the center of the Earth. So if I want to know how high above the surface the object gets, you take this radius you just calculated and subtract off the radius of the Earth, and that will give you the height that the object reaches. Let's leave it at that for today because I think that's plenty for one day. I'll give you a worksheet on this and see how you do, and then from there we'll look at, well, you see escape velocity coming up in your future. Basically applications of this equation. All right, that will do it for today then.